What is dark energy? The mysterious energy responsible for galaxies accelerating away from us. At the moment, there is no physical understanding of it in modern cosmology, but theories range from it being the result of vacuum energy to that of a negative pressure field. Perhaps this is way overthinking it. Could it be simply due to regular old gravity just from outside our observable universe? Let's construct an analogous scenario. Imagine two blind people in a decaying orbit around the Earth. Assume that their bodies are adapted to such an environment and that they can communicate and know each other's relative location. Person 2 is relatively closer to the Earth than Person 1, and as a result of their decaying orbit, falls faster as they approach. However, they do not feel the acceleration, nor do they see the Earth, and thus they assume they are being repelled, as they do not perceive of a reference point outside of their accelerating separation. This is exactly how we observe galaxies moving away from us on the cosmic scale. We assume they're being repelled by an unknown repulsive force of dark energy because we have no reference point beyond the Hubble horizon. However, in this theory, time-space, which we introduced in my previous presentation on Is Gravity Due to the Era of Time, which I suggest checking out before watching this video, is predicted to be gravitationally attracting all matter from beyond the Hubble horizon. Let's jump into the geometry and work out the math to see if our geometric calculations lines up with observation. First, we'll take a 1D line of spacetime and time-space. Remember that spacetime ends at the Hubble horizon, denoted RH, and time-space extends all the way to the cosmological horizon, denoted by RC. As touched on previously, we only have information available via light up to the Hubble horizon, which includes spacetime and a portion of time-space. Information on the remainder of time-space between the Hubble horizon and the cosmological horizon is unavailable in the form of light, but is possibly available in the form of gravity via dark energy, manifesting as Hubble's constant, an accelerative force radially outward towards the remainder of time-space. To demonstrate this, we should first know what values we're looking for. According to current models, 32% of the energy of the universe is in the form of dark and normal matter, making 68% of energy in the universe coming from dark energy. Given that gravitational energy is proportional to distance between attracting matter, this distance, RC, to the cosmological horizon should be representative of the total relativistic energy of the universe, as discussed in our previous presentation on gravity and time. We should expect, therefore, that attraction from within spacetime between all known matter and dark matter should therefore account for approximately 32% of this energy, and attraction on dark and normal matter from the portion of time-space outside of spacetime should account for approximately 68% of the total energy of the universe. This can be easily checked by simply dividing the linear portions of spacetime and timespace shown here, and remarkably they yield the hypothesized proportions of total energy. This thus providing strong evidence that dark energy is in fact the result of gravitational potential beyond the Hubble horizon of our spacetime. Note that the relationship of the Hubble horizon distance, RH, of spacetime and the cosmological horizon, RC, of timespace are related by pi. This relationship will be discussed in a future presentation on time quantization, microstates, and entropy. For now, recognize that the value of omega lambda appears to be a geometric function of space-time and time-space relationship relating to the portion of time-space responsible for the gravitational attraction of dark energy on our space-time. So the energy values line up with observation in current models, but if time-space were gravitationally pulling on space-time, we would expect to see space-time curvature throughout the entire observable universe. Turns out Einstein figured this one out with the cosmological constant, although neither he nor mainstream physics has yet to understand this value. When Einstein's field equations are applied to the entire universe, in the form of the Friedmann equation, we can get several equations which allow for solving its value. The current theory is that the cosmological constant is the energy density of space, assumed to be so because of the fact that it utilizes the density of matter in space in its calculation. However, this is inconsistent with the quantum-derived energy density, which is 124 orders of magnitude larger than that of the cosmological constant. In this presentation, I will show how the cosmological constant is actually the scalar spacetime curvature value due to gravity from beyond the Hubble horizon in time-space that we demonstrated earlier as being dark energy. In order to understand the math on this next part, I will need to run through a quick geometric analysis of the curvature jargon. Let's jump right in. Here we have a 1D curve with a number of local maxima and minima. If we want to know the curvature at these points, we simply fit the trace of a circle into them, and the curvature is 1 over the radius of that circle. If we want to know the curvature of a 2D surface with curvature in both x and y, 2D curvature, also known as the Gaussian curvature, is the product of conforming circles around the local maxima and minima as before, only in both x and y. Now if we consider a symmetric 2D surface where the conforming circles are the same radius everywhere, we simply get 1 over the square of the radius of that circle, not just at the local minima, but everywhere on the surface. Now let's look at an enclosed 2D radially symmetric surface, this being an example of a manifold, which is more generally any enclosed 2D surface. The curvature of an enclosed 2D surface is known as the scalar curvature. The scalar curvature of a surface ends up being twice that of the Gaussian curvature, which for a sphere gives the simple equation of 2 divided by the radius squared. Now let's apply this scalar curvature to the Hubble horizon surface of spacetime, with radius equal to the Hubble horizon, RH. Perhaps unsurprisingly, the scalar curvature value of spacetime is in fact equal to the cosmological constant, calculated from the Friedmann equation, and is reflected in the symmetry of the universe energy equation when taking into consideration all relativistic energy from the perspective of time-space, which includes all relativistic mass before and beyond the event horizon, as a symmetric reflection on the Hubble horizon, RH, as opposed to the perspective of gravitational attraction from observable galaxies within spacetime that we used earlier, where the distance to the cosmological horizon must be considered for the total relativistic energy. For convenience, here are the force-distance energy equations for matter and dark energy terms we calculated earlier, from the perspective of matter within spacetime. I will add that this theory can easily explain why Hubble's constant is non-homogeneous in our observable spacetime, as has been recently reported. This is because galaxy mass distribution, although somewhat homogeneous, tends to clump into galaxy clusters. We can imagine that the same behavior extends into time-space, thus not all regions will gravitationally attract equally, causing varied regions of Hubble's constant acceleration. So in summary, we have demonstrated how from our perspective in spacetime, all relativistic energy is comprised of 2 major regions: gravity from within our observable spacetime, namely regular baryon matter and dark matter, and gravity from outside our observable universe within time-space, namely dark energy. And the cosmological constant is the total spacetime curvature from all relativistic energy. Perhaps this revelation will allow for the universe to be a little less dark and a little more enlightened. Till next time, thanks for watching. Much love.